video is just more examples of solving equilibrium problems. So, first example, one of the steps in the industrial production of nitric acid is the combustion of nitrogen monoxide at room temperature, 25 degrees. So, again, remember you have two ways to see how heat is being added here. So it can be just kind of written off to the side with the plus or minus sign. This positive tells us it's endothermic, so you could also see it written as a reactant. So I think that's important for this one. So if the temperature is increased, we're going to shift to the right because it's like adding more reactant. So that shifts to the right. Okay, and we're going to do this in terms of gas pressure, so this is going to be a Kp. So we're going to have the pressure of NO2 squared over the pressure of NO squared and the pressure of O2. So a reactor is charged with 10 atm of each of NO and O2, find the partial pressure of each at equilibrium with the Kp. So I'm just going to copy that equation down just so I can put in my information. So we're going to start with the 10 atms. So because pressure is proportional to the moles in our PV equals nRT, so these are going to be proportional. I'm going to do kind of the reaction first. So since this is a 2-to-1 ratio, this is going to get used up first. So this is just like a limiting reagent kind of problem. So this will end up with none of this after the reaction has taken place. I'm going to use half of much of this, so I'm going to subtract 5 atm of the oxygen, and this was really 0, so when it reacts, because it's twice as much as the oxygen, it's going to be 10 atms as well. So that's the chemical reaction phase, and now we're going to look at that from, so that's kind of your maximums from your equilibrium. So we're now, instead of having ice, we're going to have rice. So R and then I. So this will be your initial change and your equilibrium. So we're going to have 0 for this one, and we know if we form all of this product, we're going to shift our equilibrium back this way. So the change is going to be to lose some of this, and we're not going to know how much, but we're going to do 2x. Okay. So again, it's going to decrease, so that means these are going to increase. So by x and this by 2x. So again, remember equilibrium deals with coefficients of the balanced equation. So this is going to obviously be 2x, this is going to be 5 plus x, and this is going to be 10 minus 2x. So now I'm ready to just plug everything into my equation. So when I look at my Kp value, 4.2 times 10 to the 12th is a huge equilibrium constant. So this is product favored. So it's very much skewed to this end. So taking 2x from this 10 atm is going to be minimal. So I'm going to get rid of that and just have 10 squared. I can't get rid of this because it's a 0, so that amount is not insignificant. So I'm going to have 2x squared. And again, the amount of x that we're going to lose is going to be very, very small because this is such a large number. So this is going to be times 5. So when I do the math for this one, the 8.4 times 10 to the 13th squared equals 10 squared, and you do all the math, you get x equals 1.1 times 10 to the minus 6th atm. So again, 10 minus 0.0006, even 2.2 times 10 to the negative 6th is going to be insignificant. So this would be 10.0 atm. again, adding 1.1 to this is going to be very insignificant. So this is going to be just 5 ATM. And again, there's only 2 sig figs here, so I probably should really only have 10 on this one. And then 2 times my 1.1 is going to give me 2.2 times 10 to the minus 6 ATM for nitrogen monoxide. So letter D is assuming that we got equilibrium of these values. So I am going to do my equation again. So I'm going to be starting with this 2.2 times 10 to the negative 6 ATM, 5 ATM, and 10.0 ATM. Now, I'm going to add 1.0 ATM of the NO2, so that's going to give me a total of 11 ATM. I'm not doing anything to these, so they're just going to come down. So this is going to be my, in this case, this is my stress. Look at this from a reaction point. So this is going to be my initial. Because it says this part's allowed to come to equilibrium. So my initial, my change, and then my equilibrium. So again, I'm adding more of this, so it's going to shift this direction. Ahead of myself here. So this is going to be minus 2x again, plus x, and then plus 2x. So again, these parts here are negligible because of this high value. This part, however, is not. So this one's full-blown quadratic formula with distribution and all that other craziness. So I'm basically going to get this part and this part together and do 2.1 times 10 to the 13th times my 2.2 times 10 to the minus 6 plus 2x squared equals 121. Okay, then I'm going to factor out my it's 2.2 times 10 to the 6th plus 2x, just to make it easier for me to put my terms together. So I'm doing this times this, these combined, and then this. So again, this is the math part. And again, on the exam, they're not going to have you do this. And then you're going to have to distribute this to all of your parts. So 9.4 plus 1.8 times 10 to the 8x plus 8.4 times 10 to the 13th x squared equals 121. Sorry, that's 94, not 9.4. So if I subtract the 121 from that, I'm getting negative 27. plus 1.8 times 10 to the 8th, x minus 8.4 times 10 to the 13th, x squared equals 0. So again, you're plugging in your ABC values into your quadratic formula app, and again, taking just the positive, 1.6 times 10 to the negative 7th ATMs. So again, when I add these in here, this is still going to be 11 ATM because, again, 10 to the negative 7th is going to be small. This part's still going to be 5 ATM, but this part, it is going to be significant. So this is going to be 2 times 1.6 times 10 to the negative 7th, and that is going to give me 2.5 times 10 to the minus 6th. It is enough to shift that one.